Hi everyone. I'm just going to sort of talk through the information about these parent functions. So if there is a particular function that you're struggling with, this video can help you out. You don't necessarily have to watch the whole thing through. You can just skip ahead to the whichever function or whichever concept you're kind of having a hard time with. So we're going to start with our old friends, the linear functions. And you might be thinking like y equals mx plus b. I want to remind you that the parent function is like the most basic version of a function. So a linear function is a straight line, but when we talk about the parent equation, it's just y equals x. All the other stuff, the m and the b that you would think of in y equals mx plus b, that kind of comes from some transformations that you can do to the original, which is just y equals x. This function, you'll notice, spreads out forever, left to right. It goes forever left to right. It also goes forever up and down. So it covers the entire graph, left, right, up, and down. And so that means the domain is all real numbers and the range is all real numbers. And this is a very boring function. There's no breaks in it. There's no asymptotes. So I'm just going to say none here. Okay. Moving on to our even power functions. Even power functions, really the parent equation is y equals x to the n power. And this is where n is an even number. But probably what you will think of most often is like y equals x squared. Okay, that's your most basic even power function. And then if we were to throw another even power in there, like an x to the fourth or x to the sixth, it would have the same properties that we're about to talk about. So y equals x squared, or any even power function, is going to have this parabola type shape. Technically, we only call it a parabola if it's a square. This graph does go forever left to right, so it covers all positive x values. It covers all negative x values. This graph continues forever. And so for the domain, we would say all real numbers. But you'll notice that this graph does not cover anything down below the x-axis here. It stops right here at 0. That's because when you square a number or when you raise it to an even power, the answer always comes out as a positive number, or I guess I should say a non-negative number. So for our range, I'm going to say all real numbers greater than or equal to 0. And just so you know, you could also write this as like y is greater than or equal to 0. That really says the same thing. And again, this graph does not have any asymptotes, no discontinuities. It's sort of a boring one. Okay, our odd power functions. So the big difference between our odds and our evens is when we're working with these negative x values, the even power functions have positive values because an even power will turn a negative positive, right? An even number of negatives turns positive. With an odd power function, that's not the case. So it's almost like you take that left side of the parabola and twist it downwards. So all odd power functions are going to look like this. Okay. That parent equation, again, is y equals x to some power. And right now we're talking specifically about odd powers. And you'll probably associate this with like y equals x to the third power. All right, but this will be true for any odd power. This one you'll notice is really similar to the linear function. And actually, you can sort of think of the odd power function, or I guess I should say the linear function, as being a specific type of odd power function. Because really, this is like a power of 1 up here, that x to the first power, and that's an odd power. But you'll notice that, again, the domain and range, this graph goes forever left to right, goes forever up and down. So we have all real numbers for domain, all real numbers for range, and no asymptotes. Okay, absolute value behaves similarly to these even power functions because absolute value takes all negative values and turn them positive. Now, it doesn't change their value. It doesn't, square them or anything like that, but it does have this same sort of behavior where over on the left side of the graph, your values are increasing because those negative numbers turn positive. So the absolute value function is like a mix between the linear function and the odd power, or the even power function. It's a V-shaped graph, okay? And it looks like this. Y equals straight brackets our absolute value. And you're going to notice the domain and range are really similar to what you're seeing up here because these graphs really behave the same way. So domain is all real numbers and range is all real numbers. And again, this is a nice continuous graph with no breaks or asymptotes or anything like that, no restrictions. So we would say none. Okay, the square root function is technically the inverse of the y equals x squared function. Okay, so it's like this turned on its side. But when we're talking about it in terms of functions, we really only consider the positive outcome, not the negative outcome. Because remember, when you take a square root, you can get a positive or a negative answer. But when we're talking about it in terms of functions, and I say, hey, we're taking the square root of a number, we're really only considering the positive square root. So this really looks like a sideways parabola and only the top half of it. That's what the square root function looks like. But it is really important to notice that this 0, 0 is an end point. So this graph does not have any negative values. I can't put negative numbers in here for x because taking a square root of a negative would give us imaginary values. And these graphs are only focused on real numbers. Also, like I said, we're not going to have any negative y values because when we do take these square roots, we're only considering the positive outcome. So for that reason, both your domain and range are going to be everything above 0. This graph has quite a few restrictions. It's all real numbers greater than or equal to 0, all real numbers greater than or equal to 0. And again, you could use x and y here. So you could say x is greater than equal to 0, y is greater than equal to 0. But even though this graph does have some restrictions to it, okay, so it doesn't go over here at all, it doesn't go down here at all, it only lives in this first quadrant, this isn't an asymptote. This isn't a place where the numbers get super, super close to a number and don't actually touch it. So this still has no asymptotes or discontinuities. Okay, the floor function, and I'm going to zoom this one in so I can draw it well for you. You may also know this as the step function. And there are two different types of step function, and I don't really know why in algebra we tend to focus more on the round down function than the round up, because I think mathematically they both happen, with the same frequency. But we're going to really just focus on this function here. Notice these brackets have the little tails at the bottom. And what that's doing is that's rounding your numbers down to the nearest integer. So if I put like a 4.1 in here, let me just kind of jot this up here. If I put a 4.1 inside these brackets, what these brackets are going to do is round that down to 4. Okay? Or if I put a 7.9 in here, because that's not quite 8, even though it's awfully close to 8, when I round it down, it rounds down to 7. So just so you have an idea of what this function is really doing. And so what that does is that takes all the numbers, like say between 4 and 5, and maps them to the 4. Because all of those numbers between 4 and 5, all of those decimals, are going to round down to 4. And so what that ends up doing to your graph is it gives you all these little horizontal segments. So starting at 0, because 0 would round down to 0, you get all of these numbers that would have an outcome of 0 until you hit the 1. And then when you plug the 1 in, you're going to hop up a level. And now all of a sudden your values are going to equal 1. And if I enter 1.1, 1.2, 1.3, all of those values are staying at 1 for a y value until I get to the next integer, which is 2. Okay, and so this is what this graph ends up looking like, is it's all these little horizontal segments. And it could keep going down here into the negatives as well. Okay. So the domain, this is an interesting question, and this might be harder to see from the graph, but if you think about this function, are there any values I'm not allowed to put in there for x? Is there anything that x is not allowed to be? Well, anything can be rounded down, right? Any decimal value, any negative value, everything can be rounded. So x is allowed to be anything. which means if I go anywhere on this x-axis, if I travel anywhere here, like if I want to stop right here, there should be a place on the graph that coincides with where I'm at, okay? Or if I go over here, there should be a place on the graph that coincides with where I'm at. So anywhere on the x-axis, I can find a place that this works. I do also want to point out that this graph is still a function because my vertical line test passes because of this open circle here. That doesn't really count as a point. And so these two things do not count as two separate points. So that's my domain. Now, the thing with the y values, though, is we have these funky breaks in the graph, right? We're never going to have an outcome that is a decimal, right? All of our outcomes are going to be these nice, clean whole numbers, because that's what this function does, is it turns things into whole numbers. So we have discontinuities here. We have breaks in the graph in between these integer values, okay? And so for our range, we would say this is all integer values. I'm just going to say all integers for the sake of space. You're never going to have outcomes that are not integers. And remember, integers are like your number line numbers. So this graph does not technically have asymptotes. Okay, so I'm going to just try to make this clear here that for the asymptotes, I'm going to say none. But along with asymptotes, we usually mention discontinuities, and so I think we should make a point of that. We should say that there are, and I'm going to move this over, discontinuities at integer values of x. Oops. And so what that means is that every time I get to an integer value here, there's a break in my graph. Okay, so my graph is going to break apart every time I hit an integer value. Okay, let me just get rid of that guy. Okay, let's move on. A few more of these. Okay, the exponential and the log functions, I'm going to kind of talk about these together because they are inverses of each other. And if you remember them as being inverses of each other, it's less you have to remember. So exponential functions are any time you have some number, and I'm just going to use a b to represent any number, raised to the power of x. But the really important thing here is that the x lives up in the exponent. That's what makes it exponential. Okay, these exponential graphs kind of start off slow, and then they grow very quickly. Actually, I'm going to redo that. Sorry, guys. Okay, there we go. So they start out real low, and then they start to grow quickly, and they look something like that. Okay? And we'll get to domain and range in a second, but I do want to point out that this line right here, the x-axis, is a place where this graph is going to get closer and closer and closer to, but never actually touch. That is an asymptote, okay? So our asymptote here is the x-axis, which has an equation of y equals 0, and we're going to talk about that in just a second. I will put in parentheses down here that this is the same thing as saying the x-axis. Mathematically, it's more accurate to talk about it using an equation, okay? So the equation is y equals 0. Let's kind of contrast that with the log function. So logs, the whole reason logs exist is to undo exponential functions. And so the log function looks like this. Log base b of x, and you can have any base you want. That base b is the same as the base b over here on the exponential functions. And this looks like an exponential function that's kind of been turned sideways. It looks like this, okay? So this time we get a vertical asymptote. This time we get an asymptote running up and down. And so that is the line x equals 0, which is the y-axis. Okay, so let's think about what that tells us as far as domain and range go. This graph, the exponential function, does continue left to right forever. Okay, it goes on and on forever. And so my domain here is all real numbers. But for my range, you'll notice that this graph never crosses into the negative territory. That's because I can never raise a number to a power and have it flip from positive to negative. So this graph never turns negative. In fact, it never even touches 0, because that's what this red line is telling me, that this purple graph will never actually touch that axis. And so I'm going to say for my range that it's all real numbers above 0. And notice I did not use the equal to bar this time. So when I look at the log function, those two things are exactly reversed. This time my range goes forever. My y values go up and down forever. So I would say this is all real numbers. But my domain is only the right side of the graph. My domain, I don't have anything over here with negative x values, and I never touch this 0. So for this one, I would say all real numbers greater than 0. So now let's take a look at the cube root function. And you might think the cube root function would be similar to the square root function that we talked about on the previous slide. And it is in one way, but there is one significant difference. So here's what the cube root function looks like. And this function, the difference between this and the square root is if I were to take out, this part of the graph, I would be looking at the square root function. But the cube root function does have this piece that kind of juts out to the left. And the reason for that is negative numbers are part of the domain now. Because you can take a cube root of a negative number. You can't take a square root of a negative number, but you can take a cube root. So our parent function here is y equals cube root of x. Domain now is going to be all real numbers because this graph does go forever left to right. And our range is also all real numbers because we've got positives and negatives included in there. And then this graph is nice and continuous with no asymptote, so this is another none. Okay, the inverse functions, and I'm going to throw another word on this after we draw it, but what I'm talking about when I talk about the inverse function is 1 divided by x, 1 over x. That's considered to be an inverse function. And these are the functions that form a hyperbola. So the hyperbolas kind of dance along the axes. I'm trying to draw them carefully here. Okay. And so something really significant happens here. You'll notice that based on where these arrows are located, this graph does go forever to the right and it does go forever to the left, but it misses this whole area in the middle. So we do have an asymptote here on the x-axis. I'm sorry, that's the y-axis. It's x equals 0, but that's the y-axis. And it also has an asymptote here at the x-axis. And we're going to talk about algebraically why that's true for this function. But that plays into both domain and range and asymptote. So for our domain, we want to say it's everything, all possible x's, except 0. So we have positive x's, right? We have positive x's over here. We have negative x's over here. We just don't have 0 in the middle. So this is different than saying like greater than 0 or less than 0. It's everything except 0. And then we've got the same thing going on for our range. We've got positive numbers this way. We've got negative numbers this way. So again, for our range, we're going to say all reals except 0. And then asymptotes are located on both the x and y axis, which is x equals 0 and y equals 0. Okay, and again, this x equals 0, that's the y axis. And the y equals 0 is the x-axis. And I would hope on all of these functions that have the asymptotes, so looking at this one, looking at the exponential function that we talked about a minute ago, even the log function where the asymptotes are, you should be able to look at the equation and think about algebraically why is that asymptote there? Okay, why can't x equal 0? All right, why aren't we allowed to have x equals 0 in this equation? So just food for thought. That's definitely going to be something we're going to talk about. And then the inverse square, last one, is very similar to the inverse, except it's got a square involved. And so what this does is, if we're comparing this to the original inverse function, is all of these negative x values over here, when I square them, they're now going to be positive. So basically, we're going to take this branch of the hyperbola and put it up top, okay? So this function is going to look something like this. It's like a hyperbola, but they're just side by side. Sorry, my hand's a little shaky there. I still have that asymptote here, and I still have that asymptote here. My asymptotes still exist. Actually, let me clean that up just a little bit. Okay, I still have asymptotes. So my domain, again, is all reals except 0, because this thing goes left and right forever. Just doesn't hit 0. The range is a little different, though, because it still doesn't touch 0. It still doesn't touch y equals 0, but it also doesn't touch anything underneath it, right? So we want to say everything above 0 and not including the 0. So we want to say all real numbers greater than 0. And the asymptotes are the same as they were a second ago. The x equals 0 and the y equals 0. So that's everything you need to know about these parent functions in a nutshell. Again, as we move forward, I'm going to assume that you're familiar with all of these functions and all of their properties, so that when we start messing with them, when we start transforming them, when we start doing, calculus to them, you will know the basics of how they started, okay? So if you do have questions about any of these, please feel free to ask in class anytime.